In this second section of the presentation, I want to talk about taking an information theoretic approach to visualizing uncertainty. How can we define glyphs for representing uncertainty that are in some sense theoretically based and scientifically tested? So, to give a very specific example of uncertainty, we're going to talk about temperature measurement, and the temperature measurement from sensors around Newcastle city centre. This is the measurement from one sensor. We have 1 hour in one day in May 2016. And you'll see that over the hour the temperature ranges from 9.7 to 8.7 degrees centigrade. And if you have to say, well, what's the temperature for that hour, then there are a number of ways to characterise it. You could give people the plot. You can also say what's the mean of the data, 9.1 degrees centigrade. And then what around that is the variance of that data, the uncertainty of that measurement, and variance is 0.12, or standard deviation equivalently is 0.35. And that allows you to gain in some mathematical way of a feeling for the uncertainty of the data. One of the challenges is that that's not always independent of the range of the data. So coefficient variation and index of dispersion give us ways to do that. Currently, when we visualize this data, we just visualize the value of the sensor averaged over the hour, so the mean value of temperature for 1 hour. And we use this type of glyph. These are designed to be high contrast, so black and white, so that they can stand out against any background. You can use them in 2D and 3D. And the question we started to ask is, how can we add uncertainty information to this? And this came about because the City Council said, well, very nice, but some of these sensors not so good as other ones. How can we tell which one we can rely on the most? How can we see which ones have, for example, the least variance in their measurements? So, stepping back from the specific problem for a second, talk a bit about how information theory led us to a possibility for doing this. So, information theory strictly defines how data is sent from a source to a destination, and specifically talks about how to reproduce the same signal at the destination that was sent at the source. And in visualization terms, you can imagine this as starting with digital information, that being converted by the display into optical light waves, which are sent through space, to the receiver, which is the eye and the retina, which converts that optical information into neural information, electrochemical information in the brain, and from there leads to perception and cognition. This is a great way of representing digital computer systems, but for humans it's not quite the same. So as a receiver, a human is not an ideal receiver of information, in the sense that they won't always receive the information you wanted them to, and or they'll make up their own ideas about it. And a simple example is if you send no information. If you send no information from a source to a destination, the destination doesn't do anything. It sits there and says, well, I've got nothing, I've got nothing, I've got nothing. And it will keep saying it's got nothing infinite number of times. A human being will start to make up hypotheses and generate information about the lack of information. So, okay, so maybe the receiver stopped working, maybe the sender's lost their phone, maybe they've forgotten about me. It won't be long before you're hypothesizing about why, about the cause of the lack of information you're being sent. So even without a signal, you can create a signal for information being sent without signals. What's important about this is that information in this system can be measured. The amount of information is measured, and essentially you can measure that using entropy. And entropy, in some senses, you can understand to be the complexity of the signal being sent. And we started to think, well, if a human is a receiver of information, they will be sensitive to the complexity of a signal being sent to them. And that might be a way to code extra information into our glyphs. And I'll show you what I mean more concretely in the next slide. So this is a set of shapes that Cutting and Garvin created in the 1980s, when they were trying to investigate how fractal dimension linked to perceived complexity of shape. And they did some experiments which showed that people would order these glyphs by complexity quite naturally if asked to do so. And so we started to think, well, could we use this shape complexity to encode uncertainty? And in some senses, this might be seen as a natural link, in that the more complex and broken a shape is, the more uncertainty it may be representing. But that was the beginnings of the idea. There's a similar sort of argument around radial frequency patterns, which Wilkinson and his group in University of Western Australia worked on in the late 90s, and up until today, in fact. So we came up with a set of glyph designs around shape complexity, of increasing information entropy, increasing complexity as you go from left to right. And they are set on a logarithmic scale of increasing frequency of generating signal, and that matches what we know of human perception, that it tends to be sensitive to exponential log increments in things rather than linear increments in things. So we'd expect people to be able to separate out these shapes if we asked them to. But what we need to do is test that. And so our first experiment with these glyphs was to test whether the ranking that we propose is in fact the same as people's ranking when you show them in pairs, every pair of these 7 shapes. So all 42 pairs we showed to people and asked them which is the more complex, or which represents the most uncertainty or the highest value. And we tested this in Australia, in Switzerland, and online using Mechanical Turk. And I don't want to go into too much detail on all that here, but these are the results. At the top you can see the glyphs, and you can see the hypothesized order of these glyphs. This was calculated using a technique called sample entropy, which is used for calculating the complexity of a heartbeat signal. So it calculates the signal complexity using entropy. And underneath that, the plot shows how many people in our sample population agreed with that order up to a certain glyph. So up to the second glyph with 3 lobes, almost 100% of people put those in the order there. Up to the third glyph, about 94%, and then up to the 7th glyph, about 65% of people agreed with that. Our interest was, are more than 50% of people agreeing with this? And the answer is, for all these cases, statistically yes, with a very strong p-value and power. And our test here was a one-sided binomial test of, was the mean of the response greater than 50%. And 50% may seem low, but in practice we always will use these with a key. So we won't just say, go and guess what these mean. We'll have a key beside the image saying this is the value of uncertainty that this particular set of glyphs represent. The second task we did was, well, in practice, could you use them in some way? And here we simply asked people to search in an image for them. So we took the glyph representing the lowest value, as here, and said, can you find it in the image, yes or no, whether it was present or absent. And similarly with the highest complexity glyph, was it present or absent? And in both cases, this is just the Swiss group, a majority of people got this right all the time. If it was there, they detected it. If it wasn't there, they said it wasn't there. So it's not like they're confusing the glyphs. They're certainly able to detect them with high sensitivity and a slight bias towards saying no, but nothing significant, nothing too large there. Okay, so I wanted to come back and talk about epistemic uncertainty. So this is the case where we know we could measure uncertainty, or we may be able to measure uncertainty, but we haven't got a measurement for it. But we still want to indicate that. We don't want to say we've got we don't want to say we've got a low uncertainty or a high uncertainty. We want to say we have no value for uncertainty. And that's this glyph here, although we've not tested it yet, you'll notice that it's distinctly in shape terms different from the other glyphs. And we have a number of actual other designs for this. This is active, ongoing research. Okay, I'll move on to talk about examples of the visual entropy glyphs in use now.